Okay, so we're back, and the question that we have now is, well, we know what multiplication and division are, so now what is an exponent? And an exponent is just how many times something is being multiplied by itself. So if we had 3 raised to the 2, that would be the same as 3 times 3, which we know is equal to 3 plus 3 plus 3. So you might be thinking, well, that seems a little trivial. Just because 3 is getting multiplied by 3 doesn't make there anything special about that. But exponents really help us group things pretty nicely. They clean things up quite a bit. For instance, say I had x squared. That is equal to x times x. So aha, we didn't know how to solve. We didn't know how to. We can't say what's past here because we don't know what x is. We can't, depending on what x is, we know that it's going to be added to itself some amount of times equal to what x is, but we don't really know how many times to add it. So when we have an x times x, the best we can do is simplify it up to x squared. So when we say squared, that is just a really special name we've given to something raised to the second power. Similarly, when something's cubed, that's just a special name for an x multiplied by itself 3 times. And this number up here has a special name. This number is called the index. So if I have an x raised to a power a is the index. And this can be any number, it doesn't matter. There's different things that happen though if it's different. So if I have x to the negative first, this is one of those special cases. So whenever I have x to the first, I have 1 over x. And this is really important. This is called a reciprocal. I probably am not spelling it right. I think I spelled it reciprocal. Okay. And it doesn't matter what we have. So if we had x to the negative squared, this would just be 1 over x squared on the bottom. The negative sign here just says that I put this in the bottom. So this negative sign never jumps across here because we're not talking about addition and subtraction anymore. We're talking about a complex sort of multiplication. Whenever this is up here, it doesn't affect what's down here. These are two different things. If we had x to the negative 1, it would be like multiplying x to the negative first 1 times, which would be very hard because, like, obviously if I have x raised to the first, this would just be x to the 1. However, if that negative 1, that's a negative 1, we're gonna divide that by x and nothing. So x to the negative 1 would be 1 over x. Be like 1 being divided by x. If x is to the 0, then x is just equal to 1. So a lot of times in formula textbooks, you'll have, for instance, a constant a multiplied by x raised to the n plus another constant b raised times x to the negative 1. You'll probably see this formula somewhere in an algebra textbook. Plus dot 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 plus x or c x squared plus d x, and this is where it gets a little interesting, plus e x to the 0. So when e is x to the 0, this is just our constant. So this would just be some number. It can even be 0 and not even be there. So x to the 0th, this x to the 0 index, this index here of 0 for x is going to just make it be 1. So that's an important thing. X to the 0 doesn't equal 0, it equals 1. Because if you had 0 things, you could have one way to have 0 things, which would be 0. It's kind of like the factorial. So let's look at some of the rules and how exponents work. So first we have x. Let's look at the property, which is a to the m, a to the n. So now the biggest thing here is they're being multiplied. Remember, if there's nothing in between them and they're sandwiched together, it's assumed they're being multiplied. So let's look at this. Let's say, let's use some test values here, and we're just going to say let's let m be equal to 3 and n equal to 3 as well. Well, let's change it up. Let's make that equal to 2. So we have a 3 times a to the 2. We could even expand this out into multiplication if we wanted to. Let's look at here. What do we have here? We have a term, a cubed, being multiplied 3 times. A times a times a. Remember, we do not know what a is, so we cannot. We're not going to be able to say that this is being multiplied a times because we don't know. It's not being added a times because we don't know what a is. So this is as far as we can simplify this problem down. Now, this is getting multiplied right here, getting multiplied by this quantity, a squared. And that'll break down into a times a times a times a times a. This one came from there. Okay, well, we multiply these together. We do not get a coefficient in front of it. This is 1, 2, 3, 4, 5. What we do not get is 5a, because remember that would be 5 plus, or not 5 plus, it would be a plus a plus a plus a plus a. And that is not what happened. There was never addition over here. It was always multiplication. So instead what we get is a to the 5th. And this is what we'll end up with because it was multiplied, not added together. So let's take a look at, so that's our first rule. And the rule generically is written a to the m times a to the n is equal to a to the m plus n. So an example of that would be is if I have x to the 3rd times x to the 4th, I will get x to the 3 plus 4, which is equal to x to the 7th. And let's break that down one more time and just check to make sure that's true. X times x times x is x to the 3rd multiplied by x to the 4th. X times x times x times x. Remember that this is not addition, this is multiplication. So the number doesn't go in front, it actually goes into the index. So we have an index here of 1, 2, 3, 4, 5, 6, 7. That is true, x to the 7th. Okay, now we have our second rule for exponents. And this is a to the m divided by a to the n is equal to a to the m minus n. So now, why would that be true? Well, let's take a look at this one. So we're going to let m equal to and n equal 3. And we're going to solve this. Okay, we have a, and we just let m be 2, n be 3. Well, that is just like a times a, correct? And this one's like a times a times a. Well, we can think of grouping this into ones. So we would have here, we would have this would form a group right here. That's 1, and this is 1. So we would have 1 over a times a over a times a over a. Well, a over a, it has to be changing at the same rate. So this is a being divided by something that's also the same number. So this will always be 1. This will always be 1. So this is equal to 1 over a times 1 times 1. Anything times 1 is itself. So similarly, 1 times 1 over a would just be 1 over a. So we can see, and then a over 1, remember from our reciprocals, is just a to the negative 1. So if we look at this here, we can see that if we plug this into our formula, a times m minus n, here we have our m being 2, so 2 minus 3 is equal to a to the negative 1. Okay, so let's look at this a little bit more. We have a, let's say we have a to the fourth, a to the negative second. This will break down into a times a times a times a. And this is going to break into 1 over a times a. Now this is being divided, and when we're dividing something, we got to make sure that we have two fractions over each other. So this part stays the same. It stays as a times a times a times a over 1. And this is going to get multiplied by its reciprocal, which is just a times a over 1. So when we do that, we get this quantity. We get a times a times a times a times a times a. And they're over 1 if we want to do that, but anything over 1 is just itself. So we're going to get 1, 2, 3, 4, 5, 6. We're going to have a 6 in our index. So this will be a to the 6. So let's take our formula and see if it works. Well, we're going to have a to the 4th minus negative 2. Well, a negative multiplied by a negative is a positive. 2 negatives equal a positive. So a to the 4th plus 6. Or not plus 6. Plus 2. And 4 plus 2 is 6. There we go. It checks out. So these two rules right here are basically the fundamentals of exponents. Let's look at the other rules that we have. We have this last one, and this is the big question here. Now, if we have an exponent raised to an exponent, what happens? Well, we can look at this and see what will happen. So let's use a test value. Let's let m equal 1, or let's do 2, and b equal 3. So first off, we have to start inside our parentheses. So we'll have a squared. So this is our problem. Well, if we have a squared, we really have a times a. Well, what if we have a times a cubed? Well, this is going to be equal to a times a times a times a times a times a. Now we multiply these. We don't add them. There's never any addition. So what we're going to get is our index is going to be 1, 2, 3, 4, 5, 6. We're going to get a to the 6th power. Our formula for this is going to be written a to the m to the n is equal to a m times n. So when we solve this, we're going to write this as a squared to the 3rd is equal to a squared times 3, and that'll give us a to the 6. So that is what happens when we are multiplying. And we could see this real quick. Let's use a constant. Let's do 5. Oh no, that's going to get too big. You really got to be careful with what you're choosing here when you're choosing test values. So squared, squared. 2 squared is equal to 2 times 2 squared. Well, 2 times 2 is 4 squared. Well, what's 4 squared? That's 4 times 4. That'll be 4 times 4, which will equal 16. So if we thought about this, we could have done it like this. 4 squared is equal to 16. Well, what if we did it like that? 2 times 2 times 2 raised to the power 2 times 2 would have been 2 to the 4th, which will give us 16 again. Okay, we got a final rule here, and that rule, well, we have 2 more rules actually. I lied. We have a times b to the n, and we're wondering what's going to happen here. Now the big thing here is that these 2 are not changing at the same rate. These are different. So if this is 1, this can totally be 2. They're not the same thing here. And what's going to happen is they're just going to take the same index, but they're not going to be multiplied. Nothing else happens. They just take the index that's in the outer parentheses. So if we let n equal 3, we're going to have a times b to the 3. Now let's think about that. This is ab times ab times ab. Well, remember, multiplication's commutative, so what we can do is rearrange these a's to be a times b. Well, there's nothing in between here too, so we'll have a times b times a times b. Remember, we can rearrange these in any order, commutative, so we can keep all our a's in front and then rearrange our b's behind here, and now we just count our index. 1, 2, 3. 1, 2, 3. So we're going to end up with our final answer, a to the 3rd, b to the 3rd. Now they're being multiplied. Remember here that that's going to go down here and be multiplied. You don't have to put a dot. You can just keep them, keep nothing between them. It'll be assumed they're multiplied. But you have to make sure that you keep them multiplied. It's not. This is the only operation that's going on here. It's not going to be subtracted or added. This is being multiplied together. So that was that rule, and then we're going to get here to the last rule. I'm going to clear some space off real quick. Let's go and look at what if we had a fraction, a to the b to the n. And our rule says it's going to be a to the n over b to the n. And now let's just try and see why this is true. Let's let n equal 3 again. We're going to have a over b to the 3rd. Well, that's the same as a over b times a over b times a over b. That's going to equal, remember, multiplication by division just goes across. So this will be a to the 3rd over b to the 3rd. I kind of jumped the gun there. Let me kind of go through what's going to happen. We're going to have a fraction bar that says b times b times b, a times a times a. And then we'll count our index up. 1, 2, 3, and 1, 2, 3. And those are your rules for exponents. Next, we're going to look at square roots.